Welcome students. We want to understand the three-dimensional coordinate system in this lecture. So why do we need multi-dimensional coordinate system? So for that, let's read this quote by Michio Kaku. So in string theory, all particles are vibrations on tiny rubber bands. Physics is the harmonies on the string. Chemistry is the melody we play on vibrating strings. The universe is a symphony of strings, and the mind of God is a cosmic music resonating in 11-dimensional hyperspace. Well, this quote basically is hinting towards uh, string theory, making a statement that universe is 11-dimensional. So, of course, string theory is quite debatable. So let's look at a more realistic example. So the idea is you wish to drill a hole in a sphere and you want to remove the points which lie within a circular cylinder whose axis goes through the center of the sphere. Okay. Suppose the sphere has radius 1. What should be the radius of the hole so that exactly half of the volume of the sphere is removed? So you wish to drill a hole and in the form of cylinder. So the axis of cylinder basically passes through so this is a cylinder we want to remove, hence creating a hole. So imagine this cylinder removed from the sphere, and we are asking what is the radius of the sphere such that the volume of this part, the volume here, is basically the volume removed is exactly half the volume of the sphere. Okay, it's a very meaningful question to ask. Yeah, maybe you want to construct certain objects with certain holes, and for whatever application reason, and you can basically then think about what is the radius of such a thing. So we will be able to find this in our course in a couple of lectures on how to compute this volumes when we learn about triple integrals and double integral will also do. Okay, so this calls for having a coordinate system in our plane, right? Because recall, the whole calculus was developed using the coordinate system in plane, right? So calculus of one variable was done using coordinate system in plane. So remember, recall, how did we define a two-dimensional plane? Okay, so coordinate plane. So let's recall that coordinate plane. So the way we designed the coordinate plane was we took two mutually perpendicular axes passing through a point O. So rather you start with a point O and then you draw two perpendicular axes. You choose to call one of them as x-axis and the other one as y-axis. There are conventions about the positive direction. So the positive direction of x-axis is here, positive direction of y-axis is along this arrow. And then if you talked about any point P, so point P had coordinates AB, where A was distance from y-axis. Okay, so A, the x coordinate is distance from y-axis, and B is a distance from x-axis. And now we want to generalize this idea to 3 dimensions. So what is a rectangular coordinate system in a space? So we are interested in our The space we visualize is three-dimensional, and we want to basically, for every point on the space, we want to give it a location to three, relative to three mutually perpendicular axes passing through the origin O. So let's start the construction. So we'll start with basically the following. So we choose a point O to call origin. We choose three mutually perpendicular axes. So let's say this is x-axis. Then we choose y-axis. So x, y, and then z. So these are three mutually perpendicular axes passing through origin O. So O is the origin, and these are called coordinate axes. So x-axis, y-axis, and z-axis. So let me write that down. X-axis, y-axis, and z-axis. Now, one should argue, why were x and y and z chosen in this order? So x, y, and z are chosen in the order of right-hand rule. So what does right-hand rule tells us? So if you choose x-axis and y-axis and the positive directions of x-axis and y-axis, and you move, take your right hand, curl your fingers as if you're moving from x-axis to positive direction of x-axis to positive direction of y-axis, then your thumb indicates the positive direction of z-axis. Say, for example, if I took this to be positive direction of x-axis, and I took this to be positive direction of y-axis, then this will give me positive direction of z-axis by the right-hand rule. Suppose, on the contrary, if I choose this to be my y-axis and this axis to be the positive direction of x-axis, then when I move, in that case, the right-hand rule tells me that the positive direction of z-axis should be below. Okay, so the positive direction of z-axis is chosen using the right-hand rule. All right, so just for the consistency of representation, although there will be times when we'll have to look at the space from different views, we'll keep x, y, and z in this way. All right, but we should be flexible enough to view our space from different sides so that we get a better perspective of objects we are looking for. Now, these coordinate axes, so take x-axis and y-axis. There's a unique plane passing through it. It is called xz plane because it has x and y axis in it. Similarly, if you take x and z axis, x-axis and z-axis, the plane passing through it is called xz plane, and similarly for yz plane. So you have these coordinate planes. They arise by basically, so in this case, for example, in xy plane, your z value is 0. So these three planes basically divide your three-dimensional space into 8 disjoint parts. And each of these disjoint parts are called octants. So now they are very similar to the idea we had in our plane. In XY plane, again, the best way to understand the 3 dimensions is to come back to 2 dimensions regularly and revisit the ideas. So if you do XY plane and you to consider X and Y axis, it was divided into 4 parts. So first quadrant, second quadrant, third quadrant, and fourth quadrant. So the story is similar here, where we have 8 octants. So the first octant is basically this part here, this here, and this octant basically has all X, Y, and Z all are positive in this octant. Okay, Similarly, so you can see that easily what coordinate is going to be positive. Say, for example, if I'm here, you can notice that here your y, this is positive direction of y, so this is negative direction of y, but still we are above this plane, so z is positive. We are in the positive direction of x, so x is positive, but y is negative. So there are 3 spots, right? And there are 2 possibilities, 2 positive possibilities, 2 possibilities. So 2 times 2 times 2, so 8 possibilities for, and hence there are 8 octants as well. Now, again, why do we need coordinate system? Because for a point in the 3-dimensional or point in 3D, we want to associate a number with it. All right. So the association of this number led us to do calculus, right? At least in plane, right? So we want to repeat that success in 3D. So what we have is the following. Say suppose we have x, we have y, and we have z. And suppose I have a point here. So for this point P, I want to associate a triplet A, B, and C. So A will be x coordinate. Now, what is x coordinate really? So x coordinate is, if you look how much, so the idea behind the x coordinate is how much do you have to go in x to basically plot a certain point. Yeah. So suppose I take this point and then, so if I draw it here like that, so the first one, A, is this is the, so this part is going to be your A, right? So how much you came, how many units you moved in the direction of x-axis, or in the direction parallel to YZ plane. So x coordinate essentially is the directed distance from YZ plane to P, right? So this is your YZ plane here. Let me shade it a bit. This is your YZ plane. And how much distance do you have to come? You had to come basically A away to get to this point. So x coordinate is the directed distance from the YZ plane. Why directed? Because it could be negative or positive, right? So that's why the word direction comes in. So similarly, we can talk about B, which is the y coordinate, is the directed distance from xz plane. So this part is going to be what? B. So again, the idea is if you color YZ plane, so let me color it like this. So this is a plane, and you have to come from that plane, you have to come distance B. So hence we have the following description. Now similarly, C is Z coordinate, which is directed distance from the, so this is going to be Z or C in this case. So Z coordinate, which is a directed distance from XY plane. So based on this, you get a unique location. Now, sometimes we need to see the shadow of point P in XY plane. So we call it as projection of P onto XY plane. So let's call this as a point as QAB0. So QAB0 is, so QAB0 is projection of PABC on XY plane. Now note that this projection is perpendicular projection. You're drawing a perpendicular to XY plane and then seeing where does that perpendicular, which perpendicular passes through ABC. So I'm basically drawing a perpendicular like that, and then this point will be my QAB. So similarly, we can draw a projection onto XZ plane. Let's call this as SA0C. So this is a projection, perpendicular projection onto XZ plane. Similarly, we can have a perpendicular projection onto YZ plane. So let that be represented by R, which is 0BC. Okay, so this is how it looks like. So let me use a different color pen just to indicate what is happening. Okay, so these are the projections. So now, so this is the discussion about projections. Now we have the following. We have what is called as Cartesian product. So what is the Cartesian product? So Cartesian product, that is basically Cartesian product R cross R cross R, which in short is written as R3, is essentially collection of all X, Y, Z, where X, Y, and Z belong to R. So note that this is a discussion about, so we are trying to put a coordinate system in place to understand the calculus. Is the coordinate system absolutely necessary? Well, there are certain results or certain philosophies where you can actually go in and look that the coordinate systems can be the coordinate system can be moved along as well, but in our case the coordinate system is static. All right, when you study differential geometry, for example, you would be able to see the dynamicity of the dynamic nature of the coordinate system as well. Okay, but let's come back to that later. We'll study a bit of it when we are studying normal, binormal, and tangent vectors. But okay, so now again, so this is basically, so Cartesian product. So Cartesian product, this R3 is set of ordered triplets. Yeah, so the ordering is important. Ordered triplet of real numbers. And the idea is, so this is the association between geometry and algebra. So geometry, this deserves a different color pen. So geometry, we have basically point in 3 dimensions in 3D, and algebra, the corresponding analog is a triplet. So algebra triplet of real numbers. So every algebraic object and this will represent a geometric object in 3D. So for example, now our equation will represent a geometric object. So let's look at the following. What surface in R3 is represented by x equals to 3? So let's draw this. So if we draw this, so again, if I label this as x, this is y, again, labeling x and y means positive direction of x, positive direction of y, and this is positive direction of z, then x equals to 3. What does it mean? It means you go x1, x2, 3. So 3 units here. So x equals to 3 represents this one point at least. And not only that, if you take any point here, right? So for example, if you did just 2D geometry, just ignore the z-axis for a while, x equals to 3 represented this line, right? Yeah. But now what is z here? So z is anything and everything. So all values of z are valid. So you should think about equation as a restriction on variables. So what does it mean x equals to 3? Means the restriction on x variable is that it has to be 3. Whereas y and z are free to be anything and everything. So you see that here on top of this, again, x equals to 3. So if you go up, 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 x is always 3. And what about y? Y is even below here. What about y? Y is allowed to be anything, and so is z. So you see, if I draw it slightly carefully, I will get basically a plane like this. I'm only drawing the finite part of the plane. So this is the plane passing through x equals to 3. So this plane is x equals to 3. Yeah, so all right. Now let's look at the next object. What surface in R3 is represented by y equals to x cubed? So again, let's attempt to draw this. So again, right hand rule, x, y, and z. Now I want to draw y equals to square root of x. So first I will draw y equals to square root of x in xz plane. So how does y equals to square root of x looks like in xz plane? So xz plane, I'm just drawing one part of it here. So if I have xy plane, my bad. So xy plane, y equals to square root of x looks like this. So I want to draw this, I want to translate this into this plane here. So the tilted side, the curved side is towards y-axis. So this is how, so let's use a different color pen just to emphasize what is happening. Y equals to square root of x. But now you are allowed to have, what is the value of z? There's no restriction on z. So z can be anything and everything. So if you look at this, this is how I have to give it a proper curve so that it's understood that it is this thing going on forever. I'm just drawing a part of it, right? It'll go on because this keeps on going forever, right? So this is how, this is what the surface is, which is represented by y equals to square root of x. Let's look at another example. Let's say c x squared plus y squared equals to 4. So if I just draw it in XY plane, this is essentially a circle. X, Y, sorry, Y is up here. Conventions. We need to follow the conventions. Now, so this is this in R2. Now, what about in R3? In R3, you can think about this circle moving up. So if you look about, if you try to see the same thing in R3, you can think about, if in R3, this is as if your Z-axis is perpendicular to this surface on which I'm writing, right? So, and then it's given by right-hand rule. That is not important at this stage, but if you move from X to Y using your right hand, curling your fingers, then the direction of thumb, which is outwards from the surface, gives you the positive direction of Z-axis. So how will it look like in R3? So now to draw this in R3, I would basically have to curve my axis a bit so that I get a better perspective of it. So X, Y, Z. So it will basically be a circle, right? So I have X. So this is a circle, x squared plus y squared equals to 4 in xz plane. But what is the possibility for z? Z can be anything. So I can, I can have the same kind of circle on top of it. So if you look at this, this is gonna be a cylinder, okay? An infinite cylinder which goes in both the directions. Yeah, like stretched out cylinder, right? Like say it's an infinite cylinder. So this is the representation in R3. Yeah. So yeah, let's just give some coloring shade to it so that it's clear that it is a cylinder. All right, that's I think enough of scribbling. Now let's move on to the next part. So this is the infinite cylinder, goes in both directions. Of course, I can't draw an infinite cylinder. Now we had the concept of distance in R2. So what was the concept of distance in R2? You had 2 points, x1, y1, and x2, y2. And if this was a distance, d was given by square root of x1 minus x2 square plus y1 minus y2 square. Now the question is, what about in 3 dimensions? So let's get the distance formula for between 2 points P1, which is given by coordinate x1, y1, z1, and P2, which is given by x2, y2, z2. Then the distance between them is given by, you can see that it's straightforward generalization. You have x1 minus x2 square. You have y1 minus y2 the whole square. And then there's an extra addition plus z1 minus z2 the whole square. Now let's look at a proof of this. So now think about this as basically think about this plane. Yeah. In this plane, you can see that your z is not changing at all. So as if you think about this as your xy plane really, you will have the distance d1 will be given by, and this is right angle. Yeah. So using Pythagoras theorem, this square plus this square equals to d1 square. So d1 is basically going to be the plain version of the distance formula is going to be x1 minus x2 square plus y1 minus y2 square. All right. Now, what is the total distance between these 2 points? So the distance between these 2 points is given by, again, there's a right angle triangle here. So we have d1 square plus z2 minus z1's modulus. So when you square it, equals to your d of p1 p2. Now, if you substitute your d1 square, this is going to be x1 minus x2 square plus y1 minus y2 square. And when you combine, you get this as your formula. So this is a distance formula for 3D. Okay. All right. So now let's apply and do this problem. So find a distance between P152 and P2, 2 minus 3 minus 3. So distance between P1 and P2 is given by, so let's use notation D. What is the notation we are using? Well, we are using length of P1, P2. Or we can use D of P1 comma P2 is going to be square root of difference of x coordinate square, which is 1 minus 2 square, difference of y coordinate square, which is y minus of minus, so minus 3 the whole square, plus difference of z coordinates whole square. Now, if you wish to simplify it, this is going to be 1 square plus 8 square plus 5 square. Yeah, and if we still want to simplify this, this is going to be 64 plus 1, 65, 65 plus 25 is 95. So square root of 95. Oh, sorry, not 95, 19, right? So 64, 65 plus 25 is 90. So this is the distance between these 2 points, right? Now comes a very interesting object in 3 dimensions. So this object is basically a sphere. So it's a generalization of circle, right? So the idea is, if you look at so this is how a sphere looks like. I'm not going to draw the 3D perspectives of it, but okay, so okay, yeah, so it's a 3-dimensional object. Now, what is a sphere? So sphere, basically, if you take, say, this is a center. If you take, so if you just cut the slice like that, let's look at the perpendicular slice. So if you look at all these points here, they are equidistance from this point, which is the center. So this point is h comma, this point is h comma k comma l, and this distance is r, no matter what point you take. Yeah, even here, for example, if we take a point here as well, this distance is going to be on r. So whatever lies on the surface of the sphere is at a distance r from the center at h comma k comma l. So we can now translate this into our equation, namely that what are the points? So it's collection of all these points x, y, z. What is the property of these points? The property is that distance of x, y, z. This is one point from the center h, k, l. This distance is basically equal to r. Of course, r is positive, right? If r cannot be negative, right? The distance cannot be negative, and if r is 0, that means it's just a point. So let's use this. So what do we get? So this means this is our sphere, right, of radius r. And center is also important. Center h comma k comma l. Now, what is the equation of such a thing? So we need to simplify this using distance formula. So we get x minus h square plus y minus k square plus z minus l square root equals to r. However, it looks much better if we get rid of the square root by squaring on both sides. So we get squaring on both sides. So this is your equation of a sphere of radius r and center h, k, and l. All right, so now let's look at the following problem. Show that this represents a sphere and find the center and the radius. So first of all, can I directly look at it and say, this looks like a sphere? Well, not really. Let's just simplify this guy and see how does this equation looks like. Just for the fun sake, so you see that x squared minus 2xh plus h squared plus y squared minus 2yk plus k squared plus z squared minus 2zl plus L squared equals to R squared. So what do I need? I need coefficients of x, y, and z, sorry, x squared, y squared, and z squared to be 1. And then to find out the center, I need to do this completion of squares. Yeah, I need to basically go from this step to this step. All right. So it says that, show that this equation represents a sphere. So first of all, let's get rid of x, the coefficient of x squared, y squared, z squared. They should all be 1. So this implies we have x squared plus y squared plus z squared minus 2x plus 4y equals to 1 over 4. All right, so now we need to complete the square because we want to be able to see in this format. If at all, we want to find out the center and the radius. Yeah. So let's see. So what do I do? This implies now, what do I need to add to complete the square? X squared minus 2x, middle term divided by 2 the whole square, which is 1 square. So I'm adding 1 on this side. I better add on both sides to keep equation same. Similarly, y squared plus 4y. Now I need to add what middle term, which is 4 divided by 2, which is 2, the whole square, which is 4 again. And I need to add that 4 on both sides to keep equation same. And then z squared as it is. So this part here will become x minus 1 the whole square. This part here will become y plus 2 the whole square. Then we have z square, and that is going to be 1 plus, so 5 times 4 is 20, so 20 plus 1 is, so 5 for the 21, right? So what have we gotten? We have gotten us a circle, so sorry, a sphere of radius square root of 21 by 2, right? Because after all, this is your r square. Yeah, it is positive. So it's a sphere of radius square root of 21 by 2 and center 1 minus 2 and z minus 0 square, right? So this is the equation of sphere represented by this. Now note that if we did this and you got a negative number here, then of course it won't represent a sphere. Right, so that's it. Thank you for your attention.